All right, we are going to do a brief one today, but nevertheless, we gotta keep. I mean, I don't know. We'll see. We'll see where we get. So we're still working on this problem, and I left it basically yesterday. I think we did a lot of good digging in terms of what action meant and S on D and all this kind of stuff. So today, what I want to understand is. Why. Okay, so S seems to S. Okay, S. So S. Oh no, S is these. Okay, cool. So I want to understand where is this coming from in this problem. So the problem defines S, the problem defines D, and then the problem defines G as a function of D and S, or as a product, indirect product from S on D with an action of S on D. Induced by the only possible non-trivial action of these on D. Now, I want to understand again the whole concept of induction is the way that I understood it is because we're talking about groups and subgroups, right? So if you've got an action that is defined from one group to another, and then like if so we have this group that can have an action on D, okay? And apparently this group has one only possible non-trivial action. So we need to find that one. So two things. We need to find that this group has one possible non-trivial action on D, and then I guess just for the sake of my calmness, we need to basically verify obviously that S is a subgroup of S over C3 squared. My assumption is that, based on what I've seen as well from the stuff that we've explored here, because in some examples like these things of like something over something, it has a special meaning. So we'll start there. Okay, so we'll start there. I think when we denote something like that, it's basically maybe I wanted to have, do we have the raw here? No, I don't want to see. Okay, cool. Can I just, the problem I'm having is I can't copy these because this just looks, it's just, no, okay, no, it's, yeah, but it's not, I think Grok does not really read that correctly. So I will reopen these because I want to put in the ID in here, search this data set for this ID. Exactly, because that's what I want to do. So cool. So I want to figure out, let me close some of these things. I'm working on an improved version of these, but I'll talk about this later. Close. Yeah, I'll talk about this later. Not for now, but I'll leave it open. Okay, so we're here. So I need to figure out what that means. It seems like it's, when you do these, I don't know if that's an operation or what is that. So let's figure this out. This is the problem. So let me ask these. Okay, so it actually is doing these. C times 3. Okay, so in the context, maybe I'll start a new conversation. In the context of these expression, what does the symbol mean? I have seen in group theory explanations that appears often as a way to talk about restricted groups somehow, but I have no idea. That's gonna be my my guess. Yeah, that's gonna be my guess, that this is something where you know, oh, I didn't mean, okay, it's getting confused because I didn't define S. A quotient group. Okay, so we are learning. Okay, so we need to dig into these. A quotient group, also known as a factor group, specifically if H is a normal subgroup of a group of a group G. So if H is a normal subgroup, whatever that means, so we'll need to understand that is a group G, then G over H is a quotient group whose elements are the left or right cosets of H in G, equipped with a natural group operation for, yay, I have no idea what this all means. What is a quotient group? So what, forget about S for now, and help me understand what a quotient group is. So a quotient group, also called factor group, is a way to construct a new group from an existing group by collapsing or identifying certain elements together based on a subgroup. It's analogous to modular arithmetic. Yes, okay, that makes sense. And that's what I had the feeling this was going to, because in some of the, not in here, but in some of the explanations in the earlier conversations, in the other conversations, they talk about like something modulo something. So where you group numbers that differ, you know, it was in one of these conversations. I think I saw this in, I keep forgetting which one I'm using, but I think it was in some of these explanations. Somewhere here, it was talking about like, yeah, there it is. It was somewhere here where, yeah, there you go. So Z over NZ is a cyclic group of order n. Automorphisms are multiplication by integers co-prime to n mod n, exactly. So it was, there was a modular here, but let's see. That's what kind of gave it to me. But okay. Collapsing or identifying certain elements together based on a group, on a subgroup. It's analogous to modular arithmetic in integers, where you group numbers that differ by multiples of modulo. So modulo 5 identifies 0 with 5, 10, etc. Exactly, your mapping. So this process simplifies the structure of the original group while preserving some of its properties. To understand quotient groups, okay, so we know that this is where we're doing S. So here we're doing like a modulo. So we're kind of simplifying. Okay, that's good. I don't understand why it says equals here, but maybe that's the first. Is it something that we should then try to validate? Because essentially this was, I forgot what was that about, but it was said about, I don't remember, I'll have to go back to it. But essentially it's telling us to take these and then do this modulo whatever, but I still don't understand what that is even. C3 squared. I keep forgetting this up, guys. Give me a second. I'll do a second video because I need to take this call.